Welcome to The Explainer. I'm Clara.
And I'm Theo. For a while now, the thinking has been that to make AI better, you just have to make it bigger. More data, more power.
Exactly. But today we're going to pull back the curtain and look at the incredible engineering that's happening behind the scenes. We've got a fantastic lineup of research that shows how we can build AI systems to be more efficient, more accurate, and a whole lot more secure. We'll be covering everything from clever training methods like S-Coder all the way to crucial security defenses like import snare. So that really is the big question we're digging into today, right? If just adding more data and more computing power isn't the whole answer, how do we actually make AI better? Well, it turns out a great way to think about it is like building a super sophisticated high-tech factory. That's it. So we're going to walk through the whole process, this AI engineering pipeline. We'll start with how we train smarter with smaller models, then move to optimizing for peak performance, see how these systems can learn from their mistakes, and finally, we'll look at how to guard the entire digital supply chain. It's really like following a product from raw materials all the way to the final security check. All right, so let's dive into this idea of an AI engineering pipeline. It's a really useful way to think about building these systems. It's not some kind of magic black box, right? It's much more like a sophisticated assembly line, an engineering pipeline where every single stage has to be just right. Exactly. I mean, any assembly line is only as good as the raw materials you feed into it. And for AI, the most crucial raw material is the data, specifically the instruction data that's used to train the model. The problem is, getting really high-quality data is often incredibly expensive. We're talking about needing these massive proprietary models like GPT-4 just to generate it. Which brings us perfectly to our first stop on this pipeline. How do we get those top-notch raw materials without completely breaking the bank? How do we solve this crazy expensive data problem?
Well, a really fascinating paper offers a solution for this, and it's called S-Coder. The big idea here is to explore whether we can use smaller open-source models to generate that high-quality training data for other models.
Okay, so the core concept here is something called iterative self-distillation. It sounds complicated, but the analogy is actually pretty simple. Imagine a student who starts by studying a few tough problems and then starts writing their own practice questions to get better. That's what Scoder does. You give a small model a handful of really good examples, and it starts generating its own training data. Then, and this is the cool part, it picks the very best of its own creations to teach itself how to get even better for the next round. So how does it make sure it's not just teaching itself garbage? Well, it has this really clever filtering process. First, to get some variety, it pulls data from different versions of itself. Then, it scores all that data across a bunch of different criteria to see what's actually good. And finally, it uses a pretty smart mathematical technique to figure out the exact samples that are going to have the biggest impact, the ones that will teach it the most. It's all about working smarter, not just harder, with the data you have. Okay. So we've got our high-quality raw materials sorted. Now it's time for the next stage in our factory, optimizing the machinery itself. How do we make the AI actually run tasks faster and more efficiently? And it turns out we need to look at this on two totally different levels. Right. So first, let's zoom out and look at the big picture, the overall workflow. A paper on a system called AgentX basically proposes creating an AI project manager. And this manager doesn't work alone. It has its own little team. There's a stage generator whose job is to break a big task down into manageable chunks. Then you have a planner who creates the detailed step-by-step plan for each of those chunks. And finally, you've got an executor who actually carries out the plan and does the work. And this is where it gets really clever, especially when you compare it to other approaches. You see, a system like React kind of mixes up thinking and acting all in one go. But AgentX is different. It creates that high-level plan first, and then it makes a detailed plan for each individual stage. This two-tiered, hierarchical approach is a huge deal. It helps stop the AI from getting bogged down or lost in the middle of a long, complex task, and it's way more efficient with how it manages its memory. Okay, so AgentX handles the high-level project plan, which is awesome, but what about the real nuts and bolts? I mean, how do you speed up the actual fundamental code that's running down on the hardware, on the GPU itself? For that, we turn to another paper that introduces a system called Astra. And I love this analogy. Think of it like a specialized AI pit crew for your code. It's this team of 4 different agents, and they just work in a constant loop. You've got one that writes new, optimized code. Another one immediately jumps in to test it and make sure it's correct. A third one measures its performance. How fast is it really? And then a fourth one, the planner, looks at all that and decides what to improve next. And this whole cycle just repeats, all without a human having to touch a thing. And this isn't just theoretical. The paper shows the real-world impact. When they tested Astra on critical production-level code from a widely used framework, it achieved an average speedup of 1.32 times. Now, look, a 32% boost might not sound earth-shattering at first, but you have to think about the scale. In a massive data center running thousands of these operations, that translates into absolutely enormous savings in energy, time, and of course, money. Okay, so we've got our great data, we've got our super efficient process, but things are never perfect, right? What happens when the AI inevitably makes a mistake? That brings us to our next stop, the quality control station, where we see how these systems can actually learn to correct themselves. You know, the big problem with a lot of the older self-correction methods is that you're basically asking the LLM to grade its own homework. And surprise, surprise, it's not always the most reliable judge of its own work. So this new framework called Feedback-Triggered Regeneration, or FTR, takes a much more common-sense approach. It only even tries to correct itself when an actual user gives it negative feedback. If the answer was good, it just leaves it alone. No need to fix what isn't broken. So the really crucial point here is how it makes that correction. Instead of just randomly trying one new thing, it uses this technique called long-term multipath decoding. The best way to think about this is like your GPS recalculating your route when you make a wrong turn. It doesn't just suggest the very next street, it looks ahead and explores several different possible routes all at once to find the one that's actually best for the whole trip. It helps it avoid those short-sighted decisions that just focus on the very next word. Okay, we've built this amazing, powerful, and efficient AI pipeline. It's got great inputs, it runs fast, it even corrects its own mistakes. But now we have to protect the whole thing. What are the security risks that come along with this new way of developing AI, especially when these models are constantly pulling in information from the outside world? This is where a paper on a defense called import snare comes in, and it highlights a really critical vulnerability. So AI code assistants often use a technique you might have heard of, retrieval augmented generation, or RAG, to pull in up-to-date info from external documents. The problem is, attackers can poison those documents. The AI trusts the poisoned document, and then the developer trusts the AI suggestion. It's exactly what the paper calls it, a dual trust chain, a two-step deception. And here's exactly how the attack plays out. First, an attacker goes and seeds websites like coding forums or documentation pages with information that recommends a malicious software package. Often it's what we call a typo-squatted package, something with a name that looks almost identical to a real one like matplotlib_save instead of matplotlib. Then, a developer asks their AI assistant for help. The AI's RAG system goes out, finds that poisoned document, and because it trusts the source, it suggests using the malicious library in the code. Finally, the developer, trusting the AI, just goes ahead and installs it. And that's it. The trap is sprung. So, when you take a step back and look at the whole picture, it's pretty incredible. We started with Scoder, which helps us create better, cheaper raw materials. Then we saw how AgentX and Astra can optimize the machinery at both the high level and the hardware level. We looked at FTR for quality control, letting the AI learn from feedback. And finally, import snares shows us how to secure the loading dock. It really makes it clear that building modern AI isn't magic. It's a serious engineering discipline that demands innovation at every single step. And really, that brings us to the most important question of all. Every single one of these advances shows us how to make AI more capable, smarter, and faster. But that import snare attack is such a powerful reminder. With all that new capability comes a whole new level of risk. Exactly. It really highlights that building AI that is robust, reliable, and secure isn't just a technical challenge anymore. It's a fundamental challenge of trust. Thanks so much for joining us on The Explainer.